Okay, let's go ahead and get started. So a few administrative items. First of all, we have problem set 2 graded for you. As before, these are in alphabetical order, so I'm going to pass them around. Just let them make their way about and take yours when you find it, please. I should say something about the scores on problem set 2. I've put something about the distribution here. So the mean, there were 14 possible on the score. We converted these into percentages. So the mean number of points awarded on the exam was 78%. The median is 87%. You can see from this substantial difference between the median and the mean that this distribution is going to have a kind of a long left tail. That's revealed here in the distributions we have for approximate grades. So recall that the problem sets are not curved. So 90 to 100% is some kind of A, 80 to 90 is some kind of B, and so on. So there are 27 of you who got some kind of A. Congratulations, good work. 31 of you got a B, also a very solid effort. 12 of you got a C. Might want to work a little bit harder. If you're in the D or F category here, I think you should take this as a sign that you should change something. You need to spend more time on the problem sets. You need to find a study group if you're not in one. If you're really struggling with material, you may want to try to find a tutor. If you're looking for a tutor and don't know where to find one, send me an email. I can maybe hook you up with a graduate student interested in doing that. But for sure, if you're in the D or F category here, you should be trying to make some adjustments. Okay. Questions about problem set 2 or other administrative stuff? Okay. All right, so the next administrative item I want to remind you of, I'd like to collect the expenditure diaries today. I'm going to do that at the end of class. So I'm going to stop a few minutes early and have you bring your expenditure diaries out because we have a little bit of rigmarole because we want to record the fact that you turned in an expenditure diary without actually associating your name with the expenditure diary. At the end of class, what I'll have you do is to bring your diaries up here, or at least your summaries of your diary, up in front here. I will have a piece of paper where you can write your name indicating that you've turned it in, and then turn it in. Remember, your name should not be on the diary, but there is some other information that should be. Let's see, can you all see that? So this is the, what you turn in doesn't have to be in this format, but it's fine if it does. If it's not in this format, I'd still like to see this information on it. So the information that's relevant here are sums of the different categories of expenditures that you have. So you should give us a total sum for the amount of food that you consumed over the last month. Also, just an indication of how many times you purchased food. Similarly for services, non-durables, durables, and investments. And then give us total number of purchases and your total expenditures over the entire month. So that'll just be the sum of these rows, of course. Now, in addition to these things, there's a few other pieces of information we'd like, not including your name. This formatting makes it a little obscure. On your otherwise anonymous form, tell us if you're male or female. Tell us how old you are in years, and tell us whether or not you were born in California. And so those 3 pieces of information we're going to use to try to understand variation in expenditures. Now, some of you, I think 3 of you sent me email. You're interested in helping with the data entry on this. See me after class. That's great. Okay. Questions about expenditure diaries? Other administrative items? Okay, that's great. Let's go ahead and get started then. Okay, so we started last time with a quote from the Rolling Stones. This week I'd like to pay some attention to the Beatles. Here's a quote from an early Beatles, well, not so early, an important Beatles hit, Money Can't Buy Me Love. And so the quote is close to that. I don't care too much for money. Money can't buy me love. And so this is from a song, Money Can't Buy Me Love, which was released in 1964. I'd like to take a moment to think about what these lyrics tell us about the Beatles' preferences. And so just all the problems we treat like this in this class will begin by thinking about when we have a statement like this, what's the first thing we want to try to do? What's the first step in thinking about a consumer problem? We need to decide what the appropriate commodity space is. And so what do you think, just looking at the statement here, what are the trade-offs that the Beatles are alluding to? What are the commodities that are going to be important for them? Yeah, money and love. So let's go ahead and draw that figure. So I'll do it here. So I'm going to put money here. And we should understand, we'll talk about this more later today, but we should understand this probably to mean not money per se. I don't think the Beatles were misers in the sense that they enjoyed just possessing pieces of paper with green paper. But they enjoyed the stuff that money can purchase. We'll sort of take that as given for the moment and return to that in the lecture. The other commodity, of course, is love. Okay, so those are the appropriate commodities. Now, in 1964, the Beatles were already a successful band. They'd appear on the Ed Sullivan Show. They had tons of screaming teenage fans. They were making quite decent money from their early albums. But they weren't rock gods yet, I guess you could say. They might have had a different curve that looks like this. This is speculative. I'm just going to draw a curve that looks kind of like the other ones we've drawn. And I'm going to now think about this curve and look at the statement they make here. So the statement is, I don't care too much for money. Money can't buy me love. And so I want to sort of think about that. What do you suppose that says about, can we connect that statement to something having to do with the indifference curve I've drawn here? This is a statement about their marginal rate of substitution. And in particular, a claim that they'd be willing to give up a lot of money for a little bit of additional love. So I don't care too much for money. So notice they don't say, I don't care all for money. They say, I don't care too much for money. Money can't buy me love. And what I take from that is that in 1964, the Beatles are a pretty successful band. They've got quite a bit of money. They've got a marginal rate of substitution here, which is pretty flat. So the rate at which they'd be willing to exchange. Now, this is not a statement, by the way, that they can. So the whole problem here maybe that it's difficult to buy love. But they would be willing, if a market existed for it, to give up quite a lot of money for a small amount of additional love. So this is the Beatles' marginal rate of substitution in 1964. Okay, very good. Now this is not the only statement we have in the Beatles regarding love. They wrote extensively on the subject. Here's a later observation they made in 1967, by which time they were fabulously wealthy and extremely famous. And what they said in 1967 was, all you need is love. Love is all you need. Now, I'm not sure. I think they were actually speaking more for themselves, perhaps, than for everyone. Clearly, some people need more than love. But what I'd like to think about the Beatles' statement here is I'd like to think about this again as a statement about their marginal rate of substitution. But their marginal rate of substitution in 1967, when they were much wealthier than they had been in 1964. Okay, so how could we go about thinking about this in terms of this diagram? Yeah, so they're vastly wealthier. So we'll put this over here. We'll sort of extend the indifference curve. Now, I'm not trying to claim that there's, that there may or may not have been satiation here. I think the Beatles didn't give away any of the money they said they didn't care about. So I think they still may have cared about money a little bit. But if their budget up here was this, then, whoops, I'm running this very poorly. Then their marginal rate of substitution in 1967 may have been this. And so this may be close enough to flat that it was reasonable for them to say, all you need is love. Love is all you need. Okay. So, I mean, if that's what they meant, it's not quite right because they still value money a little bit, but we'll grant them some poetic license. Okay. Any questions about the Beatles before we proceed? Okay. All right. So I'm going to come back today to the topic of trying to, of this diagram really, and to think about how people make trade-offs. We'll talk about this lecture next. Trade-offs between stuff you can buy with money and stuff you can't buy with money. Our focus today is going to be thinking about how to measure the utility that people get from a given quantity of resources when they face a given quantity of prices. And so the general topic we're going to address today is describing consumers' indirect utility functions, or their value functions. Okay, so this is a little bit of a review. Let me remind you what we're going to need for our discussion today. So let me begin with this. From our last lecture, what we did last time was we wrote down the consumer's problem, and we derived some Marshallian demand functions. So the Marshallian demand function, recall, well, actually, I won't tell you, I'll ask you. So what are the Marshallian demand functions? What is the Marshallian demand function? Let me put it differently. What question does the Marshallian demand function answer? Yes? Okay, very good. So what's your name? Say again? Teiji? Okay. So Teiji says correctly that the Marshallian demand function is the answer to the question, how much of different goods will a consumer buy given a set of prices they face and given the income they possess? So if you tell me a consumer's income, prices, and of course their utility function, the Marshallian demand function is the solution to their problem. So how much are they going to consume of X1, X2, and possibly other goods? Okay. Very good. So here's how we did it last time. And here's a version of the example we used. We said if a consumer had preferences like this, and again, you don't have to assume this particular form to get Marshallian demand functions, but it works out nicely if you do. If a consumer has these preferences, so some weight times the log of X1 plus 1 minus that weight times the log of X2, what we said the consumer would maximize this subject to a budget constraint, taking prices and income as given. Given that, the Marshallian demands allow us to predict that consumer is going to choose to consume this amount of X1. So notice we've got X1 as a function of their income, as a function of the price of the own good, if it's P1 or P2, and then as a function of this preference parameter alpha, which we assume the consumer takes as given as well. Okay, so these are the Marshallian demands we get for this utility function, and that's basically a reminder about what we did last Thursday. Okay, is that part clear? Okay, Marshallian demands map prices and income into quantities of X1 and X2 demanded. All right. So next, so you already said this. So last time we asked, given prices and income, what consumption model will consumer choose? The Marshallian demand function is the answer to that question. Today we're going to ask a different question, but a closely related one. If the consumer faces prices P and they receive some income, they have some income Y, how much do they value that income? Okay, so that's one way of putting the question. Another way of putting the question is this. If a consumer faces prices P, how much utility do they get indirectly from that money? So again, we're usually going to assume, we don't have to assume this, we generally assume that consumers don't care about money per se. This filthy lucre doesn't make them happy. It's the fact that they can buy stuff with it and that they value the stuff they buy. So the fact that you have some money in your pocket, that doesn't matter to you. What really matters is the fact that you can buy lunch with it. All right, so we're going to talk about this in terms. So the answer to this question, if you face prices P, how much utility you get from income Y, the answer to that is given by the indirect utility function. And so we'll sometimes call like this utility function, we'll sometimes call this the direct utility function. This is the utility you get directly from consumption of X1 and X2. The reason for this indirect utility function is because we give you money, and then you go off and buy stuff with it and get utility indirectly from the money we gave you to begin with. Okay, you had a question? Oh, I don't mind. Okay, and so I believe both the textbooks that you have call this the indirect utility function. There's a mathematical definition of this. I'll give you in a moment. Maybe we'll do it now. Oh, no, not yet. I'll give you in a moment. There's a mathematical definition which calls the indirect utility function the value function, which I actually think is a perfectly good thing to call it in economics as well, because it tells us how much consumer values a certain amount of income Y, given the prices they face. So your books will call this indirect utility function. I'll sometimes call it that, or I'll call it the value function. Those are synonymous. Those are the same object we're talking about, though. Okay. All right. So I told you, or we reviewed a moment ago, and talked about how we could start with the consumer's utility function with their budget set and derive Marshallian demands. I went through a laborious derivation of that last time. And my treatment last time involved assuming that starting off with a constrained maximization problem, where the consumer maximized utility subject to a budget constraint being satisfied. I then assumed in my laborious example that the budget constraint was satisfied with equality. I used that to solve for one of the goods, X2, in terms of the other good, X1, prices and income. I substituted that back into the objective function, back into the utility function, and obtained an unconstrained maximization problem. I then solved that unconstrained maximization problem by taking the first order, computing the partial derivatives and setting them equal to 0 and solving for X1 as a function of prices and income. That was how I solved the problem. That works perfectly well as long as the constraints are satisfied with equality, but it's a little bit tedious. Here's another way to do it, which I think you'll see more of in your discussion sections. That's to use the Lagrangian. So you'll see this is a little more elegant. Okay. So what we do with the Lagrangian is we start off with the utility function we had before. So this is exactly what we saw before. And what we do is we define a different function called the Lagrangian function. No surprises there. It's equal to the original objective function. So alpha log X1 plus 1 minus alpha X2. That's the original objective function. And then we add onto that thing a so-called Lagrange multiplier, which in this case we're going to use the Greek letter lambda. So we'll take lambda, and we multiply this lambda times the remaining constraint. So look what's inside here. This thing, if you set it equal to 0, is just a way of writing the budget constraint. So which the budget constraint, of course, is that P1 X1 plus P2 X2 has to be equal to Y in the Lagrangian formulation. We've just written that this way by subtracting P1 X1 and P2 X2 from both sides. So this piece inside the parentheses is really just the budget constraint. Yes? I am a single log. You're right. There should be a log in there. Thank you. Okay, Now, the beauty of this, and I'm not going to go into the mechanics of why, although you can read about it quite a bit in my all the math and economics. How do I title it? All the math you need to know to be an economist. Thank you. You'll see some discussion of the Lagrangian in there and some more discussion of the mechanics. But with this, what we do is we take the Lagrangian function and treat it as our objective function. And now it incorporates the constraints we had into the objective function in a way that's magically yields the correct result. And so if we take this object and just maximize this, now with respect, we can take first order conditions with respect to three things. The first is x1. And when we take the first order condition with respect to x1, we wind up with just this expression. We wind up with alpha over x1 from this piece of the objective function. And we wind up with lambda, or minus lambda times p1 from this piece. So this is the partial derivative of the Lagrangian function with respect to x1. Similarly, the partial derivative of the Lagrangian with respect to x2 is just alpha 2 over x2 minus lambda times p2. And then finally, when we take the first order condition with respect, when we take the partial derivative with respect to lambda, we just get back sort of a version of our budget constraint, y minus p1 x1 minus p2 x2. Okay, so these are the partial derivatives of this new function, this Lagrangian function we defined, which again is just equal to the original utility function, and then we add on all the constraints we've got, multiplying each of those constraints by a Lagrange multiplier. Here there's only one constraint, but in general we can handle any finite number of constraints. Yes?
I've seen Lagrangian written with a minus the lambda.
Yeah. So those there's an important difference between. So a lot of this math is very similar to math you might see in an engineering course or in a physics course. The difference is that here's an important difference between engineers and economists. The difference is that economists maximize and engineers minimize. So just in terms of the way we set up problems, it's very often the case that we default to one of those two things. So if you were going to try to minimize this thing, it would be more natural to make this minus lambda. Although alternatively, notice the way we've written this. We've written this as y minus p1 x1 minus p2 x2. We could have written it p1 x1 plus p2 x2 minus y. And the solutions you get from any of those methods, by the way, are the same. It doesn't really matter. As a convention, it's nice to arrange your constraint here so that lambda winds up being positive. That's convenient often and leads to fewer mistakes in the algebra, for me at least. So that's a detailed style. Okay, yeah, let's see. So if we were minimizing, though, we would want to have a minus here if we express the constraint this way. If we're maximizing, we either need to make this plus or else we need to arrange the constraint the other way around. Okay, other questions about the formulation? I'm going to go ahead and use this in a moment. You'll see that it's actually elegant and nice, I think. Any questions about how we got here? Okay, great. All right, so imprint these partial derivatives on your eyeball for a moment, and then let's go to the next slide where we're going to use them. So the trick here, I've got these three equations. I've got three equations with three unknowns. The unknowns are x1, x2, and lambda. Now, what I can do is just solve that set of three equations for the three unknowns. One thing I can do immediately is to cancel out the lambdas, and that's fine. That gets rid of one of my equations, one of my unknowns. And then I can solve for this thing quite directly. I wind up with the same thing we had before. It's that x1 is equal to alpha times your income divided by p1. X2 is set equal to 1 minus alpha times your income divided by p2. And that's the result. I think I should have another line in there to show a little more clearly how I got from this to this. Is there demand for that? It's just algebra, but maybe it's not obvious. Let me put up the screen and solve that for you. Okay, so my three equations are. So I'm going to go back one. My three equations are these. I'm just going to rewrite these to begin with. So I'll have alpha. I'm sorry. This is also not what I actually wrote there. So I'd like you to read this alpha 1 is equal to that alpha, and this alpha 2 should be 1 minus alpha. My apologies. Okay, so I have alpha divided by x1, and I said that that's minus lambda p1. That's my first equation. The second one is 1 minus alpha over x2 minus lambda times p2. And then the third equation, or the third partial derivative, is really related to the budget constraint. It's y minus p1, x1 minus p2, x2. Okay, so these are the partial derivatives. The next step in solving for the optimum is to do what with these? Set them all equal to 0, exactly. I'm going to do this in a totally cheaty way by just putting my equality in here. There we go. Okay, so I set all these things equal to 0. I move stuff around, and I get these three equations. Alpha over x1 is equal to lambda p1. 1 minus alpha divided by x2 is equal to lambda p2, and the budget constraint. Y is equal to p1 x1 plus p2 x2. Now, put on your economist hat instead of your calculus hat for a moment. We have some economics jargon to describe this quantity alpha over x1. What is that object? Where did we get it from? It came from this term here when we took the derivative of alpha times the log of x1, which in turn tells us how x1 affects utility. So this piece here is just the derivative of the utility function, the partial derivative of the utility function with respect to x1, or if you prefer, the marginal utility of x1. Yeah. So this statement here says that the marginal utility of x1 is proportional to the price p1. And similarly, of course, this is the marginal utility of x2, and so on. Okay, so now what I'd like to do is take these two equations and put a little box around them. Now I've got two equations here with a third variable, lambda. So I've got two equations and three unknowns here. I can immediately eliminate the lambda from these two by doing the following trick, which is easy to say, and it's also easy to do, but sometimes people, you may not be aware of this trick. I can just take these equations and divide one by the other. So I'm going to take this equation, I'm going to divide the left-hand side of this equation by the left-hand side of this equation. I'm going to take the right-hand side of this equation, divided by the right-hand side of this equation, and that's going to give me the following result. I'm going to have alpha